Common myth. Many people imagine a black hole as a bottomless pit, a tunnel to another dimension, or a cosmic vacuum cleaner sucking in everything around it. In reality, a black hole is an incredibly compact object with an immense gravitational pull, so strong that not even light can escape. What is a black hole? A black hole is a region of space where gravity is so powerful that escape is impossible. This happens because an enormous amount of mass is compressed into an extremely small area. For example, if Earth were compressed to the size of a pea, it would become a black hole. The event horizon, the point of no return. A black hole has a boundary called the event horizon. This is an invisible sphere around the black hole beyond which nothing, no matter, no radiation, not even light can escape. This is why black holes appear completely black. Anything that crosses the event horizon is lost forever. The singularity, a point of infinite density. At the very center of a black hole lies what scientists call a singularity, a point where matter is infinitely dense and gravity is infinitely strong. The laws of physics as we know them break down here, and scientists are still trying to understand what truly happens at the singularity. Why don't black holes suck everything in? Despite their immense gravity, black holes don't vacuum everything nearby. They exert gravitational force just like any other massive object. For example, if the sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting it just as before, only without sunlight or heat. How do we detect something that's invisible? Since black holes don't emit light, astronomers find them using indirect methods, observing how stars or gas clouds orbit around an invisible, massive object, detecting X-ray emissions from material heating up as it falls into the black hole, measuring gravitational waves, ripples in space-time caused by the collision of black holes. This is just the beginning of black hole mysteries, and future discoveries may completely change our understanding of the universe. One of the most fascinating and terrifying questions in astrophysics is, what happens if you fall into a black hole? The answer depends on the type of black hole you encounter and how close you get to it. The spaghettification effect. A horrifying death. If you fall into a stellar mass black hole, one that formed from the collapse of a massive star, you wouldn't have time to contemplate your fate. The immense difference in gravitational pull between your head and feet would stretch your body into a long, thin strand like spaghetti. This process, called spaghettification, occurs because gravity gets exponentially stronger as you approach the event horizon. The force would tear apart your molecules, and eventually even your atoms would be ripped apart. What if you fall into a supermassive black hole? Interestingly, if you fall into a supermassive black hole, like the one at the center of our galaxy, Sagittarius A star, you might not immediately feel the effects of spaghettification. Because the event horizon of such a black hole is much farther from its center, the difference in gravitational pull across your body would be much smaller. You could, in theory, pass the event horizon without feeling any immediate effects. However, you would still be doomed. Eventually, you would reach the singularity at the center, where all matter is crushed into an infinitely small point. What would an outside observer see? If someone were watching you fall into a black hole from a safe distance, they would see something bizarre. Due to gravitational time dilation, time slows down near a black hole. As you approach the event horizon, you would appear to move slower and slower, as if you were frozen in time. Your image would become redder and dimmer due to the gravitational redshift effect, as the black hole stretches the wavelengths of light escaping from you. From your own perspective, however, time would appear normal, and you wouldn't notice anything strange as you pass the event horizon, until you reach the singularity and met your inevitable end. Could there be a way to survive? Some theories suggest that if black holes connect to other parts of the universe via wormholes, falling into one could hypothetically transport you somewhere else. However, this remains purely speculative, and no evidence supports the existence of traversable wormholes inside black holes. Ultimately, falling into a black hole is a one-way trip. Whether you are stretched into spaghetti or momentarily experience a surreal, time-dilated descent, escape is impossible once you cross the event horizon. Striking and counterintuitive discoveries about black holes comes from physicist Stephen Hawking. In 1974, he proposed a theory that would change our understanding of black holes forever. Black holes are not eternal. They can gradually lose mass and eventually disappear through a process known as Hawking radiation. What is Hawking radiation? According to quantum mechanics, space is not empty, but filled with fluctuations that continuously create virtual particle pairs, one particle and one antiparticle. Normally, these pairs annihilate each other almost instantly. However, near a black hole's event horizon, something different can happen. Hawking theorized that if one of these virtual particles falls into the black hole while the other escapes into space, the escaping particle becomes real radiation, slowly draining energy from the black hole. This process leads to the gradual evaporation of the black hole over time. How fast do black holes evaporate? The evaporation of a black hole depends on its mass. The smaller the black hole, the faster it evaporates. Small black holes, such as hypothetical primordial black holes formed in the early universe, could evaporate in a fraction of a second. Stellar mass black holes, formed from collapsing stars, take much longer, trillions of times the age of the universe, to completely evaporate. Supermassive black holes, like the ones at the centers of galaxies, take an unimaginable amount of time to disappear. A black hole with the mass of the Sun would take 10 to the 67th years to evaporate, a number so large that it far exceeds the current age of the universe, 13.8 billion years. A supermassive black hole, like Sagittarius A star at the center of the Milky Way, would take 10 to the 100th years or more to evaporate, the final moments of a black hole. As a black hole shrinks due to Hawking radiation, it gets hotter and emits increasingly intense energy. In the final moments, it would radiate massive amounts of energy in an enormous burst of gamma rays, effectively exploding into nothingness. However, since the timescale for this process is incomprehensibly long, we are unlikely to observe this event in our universe's lifetime. What does this mean for the future of the universe? Hawking radiation suggests that, in the far, far future, long after stars have burned out and galaxies have faded, even black holes will cease to exist. In the distant heat death of the universe, when all matter has decayed, black holes will be the last remaining objects, slowly evaporating until nothing is left but faint radiation. Scientists have speculated about the final moments of a black hole. As it evaporates due to Hawking radiation, does it simply vanish into nothing, or could it end in a powerful explosion? The theory behind a black hole explosion. According to Stephen Hawking's theory, black holes lose mass over time as they emit Hawking radiation. This process speeds up exponentially as the black hole shrinks. The smaller it gets, the hotter it becomes, releasing more and more energy. For large black holes like supermassive or stellar mass black holes, this process takes trillions upon trillions of years, making it practically irrelevant to the current universe. For microscopic black holes, which may have formed in the early universe, the process is much faster, leading to a rapid and intense burst of energy in their final moments. At the very end of its life, the black hole reaches a point where it no longer has enough mass to sustain itself, leading to what some theories suggest could be a violent burst of high-energy radiation, essentially a black hole explosion. How powerful would this explosion be? The final moments of an evaporating black hole could release energy equivalent to millions of nuclear bombs in a fraction of a second. This would produce an enormous burst of gamma rays, which could theoretically be detectable from Earth. Can we detect black hole explosions? Scientists believe that if primordial black holes, tiny black holes that may have formed shortly after the Big Bang, exist, they could be evaporating right now. If they do, their final explosions would release a burst of gamma rays so powerful that they could be seen with gamma ray telescopes like NASA's Fermi Gamma Ray Space Telescope. So far, no confirmed black hole explosions have been detected, but scientists continue to search for sudden bursts of high-energy radiation that might be their final farewell. What would happen if a black hole exploded near us? A microscopic black hole explosion in our galaxy would be harmless unless it happened extremely close to Earth. A stellar mass black hole explosion would release an extreme amount of energy, but since these black holes take longer than the age of the universe to evaporate, we are unlikely to witness such an event. A supermassive black hole explosion is theoretically possible in the distant future, but it would take 10 to the power of 100 years, meaning the universe would be completely unrecognizable by then. The final fate of black holes. While we don't know for sure whether black holes explode at the very end, the idea remains a fascinating area of research. If detected, such an event could confirm Hawking radiation, offering direct proof that black holes do evaporate. Until then, scientists continue to scan the cosmos, hoping to catch the last breath of a dying black hole. These are not just extreme gravitational objects, they are also natural time machines. According to Einstein's theory of general relativity, strong gravitational fields can dramatically affect the flow of time. This means that black holes could, in theory, allow someone to travel into the future. How does time slow down? Near a black hole, this phenomenon is known as gravitational time dilation. The stronger the gravitational pull, the slower time moves for an observer within that gravitational field. Black holes create the most extreme version of this effect. If a spacecraft were to orbit just outside a black hole's event horizon, time for the astronauts inside the ship would move much more slowly compared to people far away from the black hole. For example, if an astronaut spent just a few hours orbiting a supermassive black hole, they might return to find that decades or even centuries have passed on Earth. This concept was dramatically illustrated in the movie Interstellar, where the crew visiting a planet near a black hole experienced 1 hour as equivalent to 7 years on Earth. Can you use a black hole to travel to the future? In theory, yes. A person orbiting a black hole at relativistic speeds, close to the speed of light, would experience significant time dilation, allowing them to leap forward in time. The closer they are to the event horizon, without crossing it, the more extreme the effect. If you could maintain a stable orbit around a supermassive black hole for a few years, centuries could pass for those outside. When you leave the black hole's vicinity, it would be like stepping into the far future compared to the time you experience. This effect is not just science fiction. It has been tested on a smaller scale. Experiments with GPS satellites, which experience weaker gravity than Earth's surface, show that their atomic clocks tick slightly faster than clocks on the ground. If this happens with weak gravity, the effect near a black hole would be magnified to an extreme level. What about traveling to the past? While a black hole could, in theory, inside a black hole, a gateway to another universe, 1800 to 2100. Black holes have long been mysterious cosmic objects, but some physicists believe they might be more than just gravitational traps. What if black holes are actually portals to other universes? The Einstein-Rosen bridge. Are black holes wormholes? The idea that black holes could be gateways to other regions of space, or even different universes, comes from Albert Einstein and Nathan Rosen, who proposed the concept of wormholes, now known as Einstein-Rosen bridges. According to general relativity, space-time can be bent and warped by gravity. If a black hole connects to another point in space-time, it could form a tunnel-like structure or a wormhole. One possibility is that a black hole's event horizon might act as the entrance to this tunnel, while a white hole, a theoretical object that expels matter, could exist on the other side. Could we survive falling through a black hole? Unfortunately, current physics suggests that falling into a black hole is a one-way trip. The intense gravitational forces inside, known as spaghettification, would stretch and destroy anything long before reaching a possible exit. However, some models of quantum gravity suggest that instead of being destroyed, matter could be transformed and ejected into a different universe. Theoretical physicist Lee Smolin proposed that black holes might actually be seeds for new universes, meaning each black hole could spawn a completely new reality beyond its singularity. Another theory from Nikodem Popovsky suggests that black holes might act as bridges, allowing matter to escape into a parallel universe instead of being crushed at the singularity. Do we have any evidence for black holes as wormholes? So far, there is no direct evidence that black holes function as wormholes or gateways to other universes. However, some indirect observations keep scientists intrigued. Some physicists speculate that certain behaviors of supermassive black holes in the centers of galaxies might hint at connections beyond our universe. The information paradox. the mystery of what happens to the information of objects that fall into a black hole, suggests that black holes could have hidden layers of physics we don't yet understand. Could we ever prove or use a black hole as a portal? To confirm whether black holes lead to other universes, we would need a theory of quantum gravity, which could reconcile Einstein's general relativity with quantum mechanics. Future observations of gravitational waves and exotic black hole behaviors might provide clues. Some physicists suggest that if a black hole were a wormhole, light passing near it might be distorted in unexpected ways, which could be detected with future telescopes. Conclusion: science fiction or science reality? For now, the idea of black holes as portals to another universe remains speculative. However, if wormholes exist, they could revolutionize our understanding of space, time, and reality itself. Perhaps one day we will discover that black holes are not just cosmic dead ends, but cosmic doorways to the unknown. Black holes are already some of the most extreme objects in the universe. But what happens when two of these titans collide? The result is a massive merger, creating an even larger black hole and sending shock waves through space-time itself. How do black holes merge? Galactic collisions. When two galaxies collide, their central supermassive black holes are drawn together by gravitational attraction. In spiral phase. Over millions of years, they slowly spiral toward each other, radiating energy in the form of gravitational waves. Final merger. When they finally collide, they release a tremendous burst of energy, merging into a single, larger black hole. This process has been observed through gravitational waves, ripples in space-time predicted by Albert Einstein, and finally detected in 2015. Gravitational waves, a new window into the cosmos. Gravitational waves were first confirmed by LIGO, Laser Interferometer Gravitational Wave Observatory, when it detected waves from a black hole merger 1.3 billion light-years away. These waves are created when massive objects accelerate, such as colliding black holes or neutron stars. Unlike light, gravitational waves can pass through any obstacle, allowing us to study cosmic events hidden from telescopes. They stretch and compress space itself, though on Earth the effect is infinitesimally small, about 1,000th the width of a proton. Since 2015, dozens of black hole mergers have been detected, confirming that these events are common throughout the universe. Could Earth ever feel the impact of a black hole merger? A black hole merger releases an enormous amount of energy, but even the most powerful ones we've detected have no noticeable effect on Earth. The gravitational waves from distant mergers are so weak by the time they reach us that they require highly sensitive detectors to measure. However, if a merger were to happen close to our galaxy, it could theoretically disrupt orbits within a stellar system. The closest known supermassive black holes in a merging process are in the galaxy NGC 6240, about 400 million light-years away, posing no threat to Earth. Conclusion: the universe is full of collisions. Black hole mergers are among the most powerful events in the universe, shaping galaxies and providing us with a new way to explore space. While we may never witness one up close, the discovery of gravitational waves has revolutionized our understanding of these cosmic giants. And with future gravitational wave observatories, we may soon detect even more dramatic and mysterious events happening across the cosmos. Black holes are often depicted in movies as unstoppable cosmic vacuums, capable of swallowing entire star systems. But how much of that is fact, and how much is science fiction? Let's separate myth from reality. Can a black hole eat the solar system? One of the biggest misconceptions is that if a black hole were to appear near Earth, it would suck up everything around it. In reality, black holes do not suck like a vacuum cleaner. They simply exert gravitational pull, just like any other massive object. If our sun were suddenly replaced by a black hole of equal mass, the planets would continue orbiting normally, though Earth would freeze without sunlight. For a black hole to pose a threat, it would need to come extremely close to our solar system. The nearest known black hole, Gaia BH1, is 1,560 light-years away, far beyond any danger. What if the sun became a black hole? Let's imagine that the sun suddenly collapsed into a black hole. What would happen? Its gravity would remain the same, meaning Earth and the other planets would continue orbiting just as before. However, without sunlight, our planet would plunge into an eternal ice age, eventually freezing over. The only real change would be the absence of solar radiation. No more light, no more heat, no more life. Since the sun does not have enough mass to collapse into a black hole, this scenario is purely theoretical. Instead, in about 5 billion years, our sun will expand into a red giant, then shrink into a white dwarf, far less dramatic than turning into a black hole. Could scientists create a black hole in a lab? The idea of creating a miniature black hole has fascinated physicists for years. Some theories suggest that high-energy particle collisions, like those in the Large Hadron Collider, LHC, could create tiny black holes. These micro-black holes would evaporate instantly due to Hawking radiation, making them harmless. No current experiment has produced a black hole, and even if one were created, it would be too small to affect anything. Should we worry about black holes? In short, no. The chance